get bigger. Another way to say it was, if you use a higher degree polynomial to approximate, then the error is going to get smaller. Okay, smaller error by using a bigger polynomial, and for sure that function f of x can be written as a power series, a Taylor series. Then f of x can be written or represented as a Taylor series. Of course, center at A. Center at A. Okay. So, what is the whole picture of this? Say you have a function, right? You don't even know what it is. You don't know much of it, but somehow you can represent that function as a polynomial plus some remainder. And you know that this remainder is getting smaller if you increase the ends, then you confident to say that this function, however weird it is, you will always be able to represent that function as a Taylor series. Okay. And there is another theorem in the book. I think they talk about the remainder. Of course, we cannot find the exact value for remainder, because if we know the exact value for remainder, this is a polynomial. You know two exact values, then you know the whole function. You don't know exactly, but at least you can approximate or can have an upper bound for this. And the remainder theorem saying this: if f n, let me see the rules of f n of f n plus 1. Oh, n plus 1. You take the derivative n plus 1 time of x. Okay, and this is less than or equal to m. Okay, on the interval of x minus a less than d. And d here is smaller than the radius conversion. Okay, then you can say that the remainder will be less than or equal to, let me see if they have equal. Yeah, m, let's pick m right here, over n plus 1 factorial times x minus a to the n plus 1. I think that was the absolute value. Let me double check. Yes, because everything is positive. Okay. So if you can calculate the, you can write the function as Taylor series plus the remainder, and you take the derivative of that function n plus 1 time, you can find the boundary for the remainder, then you can guarantee that the error that you are making is no more than this. Okay? Say, let me give you an easy example. Say, f of x. We know everything about this already, but just right now. F of x equal to e to the x. The reason why I chose this example, because what? E to the x really is always e to the x all the time. And say your interval for x is between -1 and 1, then this is your interval. Okay, then f n of x is still e to the x. Okay, you are looking for the function between just -1 and 1, because I want to find a boundary for this. Okay, so f n of x, n plus 1 of x is still e to the x, so it's going to be less than or equal to e, right? So if you use like n term, it's like 100 term, you want to approximate f of x using 100 terms, it's going to be what? E to the x is approximately equal to 1 plus x plus x squared over 2 plus x cubed over 3 factorial plus that all the way to x to the 100 terms, so x to the 100 over 100 factorial. Okay, of course more, but you only use that much to approximate e to the x. Of course, whenever you approximate, you're going to make the error, and the errors are 100. Gonna be no more than, this is my m right here, right? Gonna be no more than e over 101 factorial. Okay, times x minus a right here. I use the center at 0, so times x to the 101. Okay. So if you plug in here, you want to calculate what? e to the say 0.5. And then you can use 100 term, you get 1 plus 0.5, 0.5 squared over 2, 0.5 cubed over 3 factorial, all the way to 0.5 to 100 over 100 factorial. You're going to have a very good, really good approximation of e to the 0.5. And what is the error that you make when you make that approximation? This is the error. It's e over 0.001, 101 factorial times 0.5 to 101, which is extremely more in a small error. What if I only use, actually in here I can only use 3 or 4 terms. So if I use 4 terms, okay, 1 plus x squared over 2 plus x cubed over 3 factorial, right here, 2 or 2 factorial, same thing. Okay, to approximate, then my error is what? R4, be e to the 4, or you can use, you don't know e yet, and e is 2 point something, you can less than or equal to 3. Okay, good. 3, you know 3, right? Say, but if people argue that, oh, what is e? I don't know, so use 3. Okay, 3. And 3 over, for sure that remainder will be less than, say here, m, which is whatever number you have over there, over, this is going to be 4 factorial, and then this is the 4, so you approximate what? E to the 0.5, and 1 plus 0.5, 0.5 squared, 0.5 cubed, is over 2, this is over 3 factorial, 0.5 to the 4, this is m, whatever the upper bound you plug in, you have the error. Or for an iGlam, that much is a very good, very good approximation of e to the 0.4. What if you want to approximate e? Then you plug x equal to 1, right? E to the 1 and just e, then iGlam you use like 4 or 5 decimals. It's very good approximation. Okay. And whenever you do approximation, the next question is always, what was the error? Right? What's the maximum error you may make as you do approximation? And this is the formula. Okay, and then for, I think, one more, I'm going to show you another power series. That's the book included in this section. It's called the binomial series, I think. Let me look for the name of it. Binomial series, yeah, I was correct. Let's recall back to pre-calculus. If you still have in your mind, the binomial theorem say this. Binomial theorem. You have this. X plus y raised to the n is equal to what? Let me change this to the k and make it like our book, okay? Because in pre-calculus we use n in here, but in our calculus book we use k. So let me change it to k. Okay? So this is k to 0 x to the n plus k choose 1 x to the n minus 1 times y plus k choose 2 x to the n minus 2 y. I use k already, so not n. K here, k there, then y squared plus da da da. The last term will be k choose k, the term right before the last term. So x, y to the k minus 1, and last term going to be k choose k, y to the k. Okay. So let me explain all the notation, and then move on from there. In the combination, this notation, k choose n means what? K factorial divided by n factorial times k minus n factorial. And you know n factorial already. For example, 5, 3 means what? 5 factorial divided by 3 factorial and times 2 factorial. 5 on top, and then 3 factorial, and then 5 minus 3. Okay, factorial. This comes from combination. You talk about discrete math. This is how many times you choose 3 items out of 5 items when order doesn't matter. You have, say you have 5 markers, okay, and you want to choose 3 markers out of 5 markers, okay, and this is how many ways, okay. And this is a formula. We write that way. So in short, we write this: sum This is k, okay? I use k for math. Let's just get back to n because this is how we write in pre-calc, but in calculus 2 they write k, exponent k. So this is what? K choose n of x to the k minus n times y to the n run from 0 to k. That's what it is. So you put the 0 right here is what? K choose 0 x to the k times y to the 0. So this first term, k choose 1 x to the k minus 1, y to the 1, so forth and so on. Okay, binomial theorem. Okay. And the expression of this, let me rewrite one more time. K n is k factorial divided by n factorial times k minus n factorial. And in short, you can cancel out one of those is what? K times k minus 1 times k minus 2 times all the way to k minus n plus 1, and then divided by n factorial. Okay. That was a theory we learned in pre-calculus, and I'm not sure if everyone goes through the same pre-calculus to get to here, but at least I'll try to write back so you have a chance to see it. Okay, if you don't feel comfortable with it, please look it up in your pre-calculus book, or just feel free to shoot me an email, and then I will give you a link to where to look at. Okay. So if the question is not like explain to me the whole thing over, is that question, then it's gonna I won't be able to answer that. But if some part in here that you don't quite understand, let me know. Just ask me, then I'm more than happy to explain it to you, back to you. Okay, now we're gonna give you the binomial series in Calc 2 version. Okay, so let me keep the first one right here. In Calc 2 version, we replace y by 1, okay? Oh, let me just rewrite in here. Sum of k choose n run from 0 to k of x to the k minus n times y to the k, or y to the n, okay? And of course, spend it up. On Calc 2, we replace y by 1. We got what? X plus 1 raised to the k, sum k choose n run from 0 to k, what? X to the k minus n, right? Of course, y is 1. X to the k minus n. Oh. Let's see. I'm sorry. We replace x by 0, okay? It's the same, so I should write this way. That'll be easy for you. K right here and then n. K minus n. It's the same because k choose n is the same thing as k choose k minus n. Let's write it this way. There's nothing wrong with that. Just try to match up with the book. Okay, so let's fix it the same. Instead of in here, I should say let x go 0, but I say y go 0. So let y go 0. X go 0, you have all the way y, then it's y to the k minus n. Okay, but the book throw x. So after that, you replace x by y, you have the answer. Right this way. Okay, this is our calculus 2 version. They just replace one variable by 1, and they have this. And let me expand it out. You have what? K choose 0 x. So this is n right here. N right here. Fix that a little for me. I make a mistake on that. K0 x to the 0. K1 x to the 1. K2 x squared plus k choose 3 x cubed. Okay. So for now, you don't see any advantage of the Calc 2 version yet. In Calc 2, we claim that the exponent k right here may not be the whole number, may not even be positive, could be any kind of number, could be positive or negative. And it turns out that what? This combination notation doesn't make much sense anymore. So we're gonna write the implication form of it. So we say what? K20 is just like 1. Yeah, so 1 x to the 0, which is 1. Okay. K choose 1 is k x, right? K choose 2 is k times k minus 1. And over 2 factorial x squared. Okay. So k choose 3. This is what we mean by k choose 3. K times k minus 1. I keep writing next. What's wrong with me? K minus 1 times k minus 2. You see? Choose 3 means you have 3 factors. Okay? Divided by 3 factorial and then x cubed. So the next term, k choose 4 means what? K times k minus 1 times k minus 2 times k minus 3 over 4 factorial. Keep going. Okay. And for count 2 version, k could be any number. Okay. So let me rewrite the whole thing. Make sure that you all get the right version, because I try to link what you're learning here with what the binomial theorem that you have in brief calculus, and it turns out that 2 different books use 2 different notations, so it may get confusing. So let me rewrite the whole theorem like this: x plus 1 raised to the k in count 2 version is equal to this: 1 plus kx plus k times k. Keep running that. K minus 1 over 2 factorial x squared, k minus 1, k minus 2, 3 factorial x cubed, plus x on the side, k minus 1, k minus 2, k minus 3 over 4 factorial x to the 4 plus da da da. So the rule is what? Whenever you have exponent, then what? That's exponent k, right? So well, first of all, always start with 1, and then exponent k times x, and then what? Going to be 2 factor k, and then go down 1, k minus 1 over 2 factorial x squared, and then 3 factor k minus 1, k minus 2 over 3 factorial. Keep going. Okay? And that will help us to find the power series for more type of function. For example, you have square root of x plus 1. Then you can think of it as x plus 1 raised to the 1/2. So in this example, k is 1/2. And you want to find the power series of this. Look in here. 1 plus 1/2 x plus 1/2 times 1/2 minus 1 over 2 x squared plus 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial x cubed plus da da da. And then you can calculate those coefficients, the numbers. You have a power series. Okay. Say, what if you have this? X minus 1 to the 1/2. So I said the plus 1, this is minus 1. What do you do? I see what's different. Our book didn't write x plus 1. Our book write 1 plus x. So that's why the order that match up when I write x plus 1. It doesn't matter. X plus 1 and 1 plus x is the same. Okay? So in here is a square root of x plus 1 is like this. X plus 1 to the 1/2. Okay? So this one right here, you have to modify this a little, make it look like a variable plus 1. So this is was that negative of was that how do I think of it? 1 plus x, right? So 1 plus x. This is negative 1 plus x. So this is negative of 1 minus x. Okay. Oh, I can write it this way. X plus negative 1, is that right? Does that work? And let's raise to the 1/2. No, I cannot write it that way. Let me think. I have to write this way. Negative of negative x plus 1. That would be better. So I think as our book way is better, but that anyway, if I write this way, that'd be okay. And raised to the 1/2. Negative with negative x is x, and then minus 1, yeah? And this is f of x, right? And this is what? Negative f of negative x, and then raised to the 1/2. Okay? No more 1/2. Am I correct? Yes. Looks right to me. And then f of negative f of negative x right here. You would is negative x, negative x, negative x, right? And then let's see if I think I make some mistake in here. Let me try to fix it. X minus 1 to the 1/2. Can I fix that? No, that should be right. Let me fix that. Okay, this problem. I should go with the book where this is 1 plus x, and then you have the whole thing is the same, right? So the problem that you can do with similar is what? Square root of 1 minus x. That would be better. Okay, this is f of negative x. That's what I'm trying to say. I wrote x minus 1. I think that would work out too, but let's go with this one first. F of negative x, and that will work out. And this is what? Negative x plus 1 to the 1/2. That looks easier. Okay, so this is 1 plus 1/2 to the negative x plus the whole thing right here, 1/2 times 1/2 minus 1 to the 2 negative x squared, 1/2, 1/2 minus 1, 1/2 minus 2 to the negative x cubed, so over 3 factorial. Keep going, and of course you simplify, you have the answer. Okay, you see it's in here. Be very careful with your algebra. I myself may make mistake too, and if you have something that looks kind of similar, make sure that you modify it correctly to have the answer. Okay, so chances a little in the book ways you better, instead of writing x plus 1 like the way I write, it's actually the same if you write 1 plus x, but now it looks more natural if you read the book. It doesn't matter, it's the same thing. Okay, it's 1 plus x. Just might have it right, x plus 1. 1 plus x, and because all the example in the book they start with this type, so you go with this. Okay. Let's try another one. Let me look for one. Okay. How about this? 1 over square root of, how about say 4 minus x. Okay. So first of all, I would try to make it look like 1 plus some variable instead of 4. Okay? So this is 4. I've got to factor out the 4, so 1 over square root. I factor out the 4, I got 1 minus x over 4. Okay? So this is 1 over 2, because square root of 4 is 2. Of square root of 1 over square root. 1 over square root of 1 minus x over 4. Which is 1/2 of 1 minus x over 4 raised to negative 1/2. Okay, square root in the bottom is negative 1/2. So this is the same thing as 1/2 f of oh, we have the formula right here already. Okay, 1/2, right, and then what? 1 minus x over 4 raised to the negative 1/2. Apply the formula right here. Of course, we have 1/2 as a constant outside, so we write 1/2 outside. Okay? And what? 1 minus x over 4 raised to a negative 1/2. So my k is negative 1/2. We start with 1, and then what? Plus negative 1/2 x plus negative 1/2 times negative 1/2 minus 1 over 2. It's not x. Now I make another mistake right here. It's not x. It's going to be x over 4. Let me rewrite it. 1, right? The second term is what? K times the variable. And here, not the variable x. The variable is negative x over 4. So k is negative 1/2. Okay? and the variable is negative x over 4. Be very careful, okay? And then plus, the third term is what? K is negative 1/2, then negative 1/2 minus 1 over 2 factorial, and this is my x, okay? Times negative x over 4 squared, and then another term, negative 1/2, negative 1/2 minus 1, negative 1/2 minus 2 over 3 factorial, and then times negative x over 4 cubed, and plus dot dot dot. And don't forget that you got 1/2 right here multiplied to all the terms.